talk about the moment of inertia. The moment of inertia is telling me about the resistance to a change in rotational motion. So if I thought back to linear motion and summing up the forces in the x direction, say equal to ma, mass times acceleration. Mass is that inertia quality, that resistance to a change in linear motion. When we get to rotational motion, we got to do it a little different because we talk about the moment of inertia, which is going to be dependent on both the mass and the radius. Let me give you a quick example. So if I take this bar and it's got two masses on it and I spin it, you can see I can spin it pretty fast when those masses are close in, but without changing the amount of mass on the bar and only changing where that mass is distributed, so distributing that mass further out, all of a sudden that bar gets a lot harder to spin, and so I'm spinning it slower. You can also think back when you played t-ball or baseball or something, they'll talk about choking up on the bat, meaning if I hold the bat closer to that massive end, it's easier to swing than if I hold it far from that mass, okay? And so we're going to talk about moment of inertia just in general, that the more mass I have, the more inertia I have. The more that mass is distributed far from the axis of rotation, the more moment of inertia I have. The harder it is to change that rotational motion, meaning that angular acceleration will be smaller due to the same amount of torque. So when we get to actually using moment of inertia, there's a couple different ways we're going to use it. And so it really depends on what we have. So if I have a single point mass, meaning the object size is much smaller than the radius that it is occupying, we can talk about it as a point mass, and we can say the moment of inertia is equal to the total mass times the radius squared, and that radius is the distance from the axis of rotation to the center of mass of that point mass. If we have multiple point masses, so in our example here I had 2 point masses, all I need to do is find the moment of inertia for each of those values and add them up to get the total moment of inertia. Now if I have a continuous object, such as this meter stick here, I'm going to have to go ahead and integrate the mass function times radius squared. Okay, so we're going to take a look at how we do that, but if we have a continuous object, we are going to need to integrate. If I have multiple objects, all I need to do is find their individual moments of inertia and add them together. So in this case, I have 2 point masses, and then I have the meter stick. So I would have to find the moment of inertia of the meter stick using integration, and then I would need to find the moment of inertia of my 2 point masses using my point mass, and then add those 3 values together to get my total moment of inertia of this object. Now, some of them are just going to be given to us. So for instance, if I have a solid sphere like a bowling ball, or if I have a hollow sphere like a basketball, they'll just be given to us. And so they've already done this kind of integration process for us in these 3-dimensional or 2-dimensional cases where we have like a disc or a solid cylinder. So you can imagine like this would be our solid cylinder, also known as like a disc. Or if we have a thin-walled hollow cylinder, so that would be something that looks like this, or a hoop. And you'll notice that the hoop is just mr squared, and that's because it's essentially a point mass that's stretched out along that same radius. So since all of the mass is at the same radius, I can consider it a point mass. Kind of a cool thing there. So this is just our general intro to moment of inertia. We'll be doing some more problems with each one of these types a little later on.